Welcome back to the deep dive. We're here again to unpack complex topics, digging into the insights from the sources you provide. Today, we're kicking off a brand new series, which we're calling Beyond Transformer, the next generation of sequence and language modeling. And for this first deep dive in the series, well, we need to set the stage. We're tackling a real giant in AI, the transformer. It's an architecture that has, completely reshaped deep learning. But like any powerful tool, it's starting to show its limitations, especially as ambitions grow.
Indeed. And transformers have had immense success. There's no denying that. They've become almost synonymous with modern deep learning, especially for things like language modeling. They've revolutionized so much. But yeah, our mission today is really to critically examine the inherent bottlenecks. These are the challenges pushing the field, driving this urgent need for alternatives. Alternatives that are more efficient, more scalable, particularly when you're dealing with really long sequences. Understanding these limits is key. It really lays the groundwork for what we'll discuss later, state space models, other new architectures designed specifically to overcome these hurdles.
It really is hard to overstate their impact, isn't it, Transformers? Just thinking back a few years, the idea of AI writing coherent text or understanding complex code felt almost like science fiction. Now it's almost commonplace. And so much of that is down to the transformer. They're just synonymous with the big breakthroughs in NLP and even beyond NLP now. So what was it? What made them so dominant? How did they usher in this era, leaving older things like RNNs or LSTMs sort of in the dust?
That's the crucial question. And the answer really hinges on one core innovation: the self-attention mechanism. Before transformers, you had models like recurrent neural networks, RNNs. They process sequences step by step, token by token. Think about reading a very long book, one word at a time, trying to connect something in chapter 1 with something in chapter 20. It's tough, right?
Yeah.
RNNs really struggled with those long-range dependencies, remembering information far apart in a sequence.
Right, the classic vanishing gradient problem where the signal just kind of faded over distance.
Exactly. Self-attention fundamentally changed that paradigm.
Huh.
It allowed the model to dynamically weigh the importance of every other part of the input sequence, and crucially, regardless of their distance. So instead of that sequential scan, imagine the model instantly looking at every word in relation to every other word simultaneously. It assigns an attention score, like a focus level, between all pairs. This ability, capturing global dependencies directly in essentially one computational step, that was the game changer. It meant information from the very start of a long text could directly influence processing way at the end. That was a massive hurdle for older models. This break from strict sequential processing just unlocked huge performance gains.
So it's not just what it could do, linking distant things, but how it did it. That direct, non-sequential access to information sounds like the real leap.
Precisely. And that direct access, that non-sequential nature, had another critical benefit: parallelizability. Because the attention calculation for each token can happen more or less independently, you don't have that strict step-by-step dependency. This meant you could throw massive parallel hardware at it, like GPUs, and speed up training dramatically. This parallel processing capability is really what enabled the scaling laws we've seen. It allowed us to build models with billions, now even trillions, of parameters. And we've seen them excel everywhere. State-of-the-art machine translation relies heavily on them. The large language models we interact with daily, GPT, Llama, and others, they're transformer-based. Code generation, understanding complex code structures. That needs long-range understanding. Even things like computer vision with vision transformers, or biology like protein folding with AlphaFold, transformers became the dominant architecture.
Okay, so undeniable success, revolutionary even, but you mentioned limitations, inherent bottlenecks. These are now becoming more and more apparent, right? Especially as the field pushes for bigger models, longer context windows, more sophisticated tasks. So let's unpack those. What are the core architectural constraints that are making people rethink the transformer even while it's still on top?
Yeah, this is really the crux of the transformers dilemma, as we're calling it. The primary constraints, the biggest ones, they stem directly from that core mechanism: self-attention. It's incredibly powerful, yes, but it's also inherently costly, computationally and in terms of memory. A real double-edged sword. Okay, first bottleneck: quadratic computational complexity during training. We just talked about how self-attention calculates pairwise interactions between every element in the sequence. Every token looks at every other token. So if your sequence has length L, the number of those interactions, the amount of computation needed for attention, it scales with L squared, OL2. And quadratic scaling gets out of hand fast. Imagine training on, say, a 10,000 token sequence takes an hour. Doubling that to 20,000 tokens doesn't take 2 hours, it takes closer to 4 hours, is just for the attention part. Double it again to 40,000, you're looking at maybe 16 hours. Whoa, okay, so it explodes pretty quickly. It's not just a linear increase. Exactly. It's an explosion. This OL2 cost during training becomes a massive hurdle when you want to handle really long sequences. Think entire books, legal archives, massive code repositories, hours of audio. It makes training on these contexts prohibitively expensive, incredibly time-consuming. It pushes compute costs into the stratosphere. It fundamentally limits the practical length of sequences you can even afford to train on, regardless of how much hardware you have. It becomes a hard wall.
So it's not just about cost, it's almost like a physical barrier imposed by the algorithm itself. You can't just throw infinite money at it past a certain point because the time becomes astronomical.
That's a great way to put it. It's a diminishing returns problem taken to an extreme. More compute buys you less and less in terms of sequence length capability. You run out of practical time and budget. All right, now the second major bottleneck. This one pops up during autoregressive inference, and it's mainly about memory. Autoregressive inference is when model generates output one token at a time, right? Like predicting the next word in a sentence based on all the words that came before. To do this, transformers need to keep track of the representations of all the previous tokens. They maintain an explicit cache, often called the KV cache, key value cache. This cache stores the intermediate key and value vectors computed by the attention layers for every single prior token in the sequence. Each new token generated needs its representation added to this cache, and the cache is needed for the next token's attention calculation.
Okay, so it needs to remember everything that came before, explicitly. How does the cost scale here? Still quadratic?
No, thankfully not quadratic here. The memory requirement for this cache grows linearly with the sequence length. So OL memory. Double the sequence length. You roughly doubled the memory needed for the cache.
Linear sounds better than quadratic, but I suspect there's a catch.
There is. While linear growth is much more manageable in theory, in practice, GPUs, the hardware we use for this, have finite memory, often quite limited memory, like 40 GB or 80 GB on high-end cards. This linearly growing cache can eat up that memory very quickly. A large model with, say, a 4096 token context window might already use a huge chunk of GPU memory just for this cache. If you try to push that to 8192 or 16K or 32K tokens, you very quickly exceed the physical memory available on the device. This imposes a very real, very hard limit on the context window that can be processed effectively during real-time generation. The available GPU memory literally dictates how much history the model can keep track of before it runs out of space and effectively has to start forgetting things.
And that's what users experience, right? When a chatbot seems to forget the start of a long conversation, that's the KV cache filling up.
Often, yes. That's a direct manifestation of this OL memory bottleneck during inference. The model simply runs out of room to store the context.
Okay, so we have OL2, compute and training, and OL memory and inference, both leading to hard limits on sequence length. What does this mean beyond just efficiency? How does it affect the way these models handle information, especially for ongoing continuous tasks?
That's exactly the next level of the problem. These costs aren't just about speed or hardware limits. They fundamentally shape how transformers interact with context. First, it leads directly to the finite context problem. As we just discussed, because of that cache mechanism storing every prior token representation up to a limit, transformers have a built-in hard cutoff on context length. Once you exceed that cache size, the information from before that point is just gone. It cannot be accessed. This creates a really interesting contrast with, say, human memory. You could almost describe transformers, maybe metaphorically, as being like databases. They treat every single observation, every token, as an important piece of data to be filed away perfectly for precise recall later. Within their window, they're designed for high-fidelity retrieval. That's why they're so good at tasks needing exact memorization. Finding a specific fact in a document, recalling a precise line of code, answering a question based on verbatim text they just saw.
A database, I like that analogy. Precise, but limited in scope. And humans, well, we're definitely not like that. Our memory feels very different.
Exactly. Humans are, as some researchers put it, hopelessly bad at exact memorization on that scale. We can't recall entire documents verbatim, yet we seem to maintain a much longer history of fuzzy context. We remember the gist, the overall narrative, the feeling, the key takeaways from experiences long past, even if the precise details fade. We summarize, we abstract. And this is where other architectures, particularly the recurrent models like state-space models we'll get into, potentially offer a different approach. They are designed, hypothetically, to maintain an infinitely long but fuzzy memory of the past. They do this by continuously updating a fixed-size internal state, a summary, rather than storing every single past detail.
Like keeping a running summary in your head rather than a perfect transcript.
Sort of, yes. A constantly evolving compression of the past. This qualitative difference means transformers can struggle with tasks that really need that long, persistent summary of context. Think long dialogues, summarizing huge amounts of information coherently, tasks where the shape and flow matter more than recalling every single word, that chatbot forgetting the start of the conversation. That's the finite context hitting its limit. The model literally can't see beyond its window.
So it's a fundamental difference in how memory works.
Right.
Precise but finite versus potentially infinite but fuzzy.
That's a good way to frame the theoretical difference. Now, there's important nuance here, too, which is the practical challenge of length generalization issues. While recurrent models like SSMs theoretically offer that infinite fuzzy memory via their fixed state, getting them to actually use that capability effectively on sequences much longer than they saw during training has been tricky. We've seen this in practice. For instance, early versions of Mamba 2 checkpoints, a really promising SSM we'll cover in detail later, they struggled significantly. They became, and I quote the sources here, virtually useless for sequence positions beyond their training context length, maybe 2048 tokens. What happens is, when they encounter these much longer sequences, they enter unexplored states. Their internal memory state drifts into territory it never learned how to handle during training, and performance collapses.
So it's like they have the capacity for long memory, but they haven't been trained how to use it effectively beyond a certain point. Like that marathon runner analogy, trained for sprints, collapses in the long race.
Exactly. But here's the encouraging part, and why it's seen as an unrealized potential, not a fundamental flaw like the transformer's hard limit. The sources show this can be fixed, often quite easily. Techniques like state passing during training explicitly teach the model how to carry its memory state forward across long sequences. And sometimes, even just a tiny amount of post-training focused on longer sequences can make a huge difference. Like for Mamba 2, just 500 steps of post-training, maybe 0.1% of the pre-training compute, allowed it to generalize incredibly well, up to sequences of 256,000 tokens. So it demonstrates that while length generalization is a challenge for recurrent models, it seems solvable. It's not an inherent architectural brick wall like the Transformer's OL2 compute or OL cache memory. It underlines that truly mastering long sequences is tough for any architecture, but the pathways might be more open for recurrent models.
Okay, that's a critical distinction. Solvable problem versus fundamental architectural limit. Now let's shift gears slightly. Beyond compute and memory, you mentioned the way transformers process data introduces other limits, specifically around inductive bias and this whole issue of tokenization. This sounds really fundamental.
It is. It gets to the heart of what the model is predisposed to learn and how it interacts with raw information. Let's talk about inductive bias. Think of it as the model's built-in assumptions or tendencies. How does it naturally approach a task? Because transformers use that explicit KV cache for every prior token and compute attention between all token pairs, their core inductive bias is to pay attention to individual tokens. The model inherently wants to focus on, recall, and relate specific discrete units of data. Now, this bias works incredibly well when those individual tokens are already semantically meaningful. Think about words in English, or common subwords created by tokenizers like BPE. Units like transform, attention, they carry distinct meaning. The model can learn to assign importance to these meaningful chunks effectively.
Right, you mentioned BPE earlier, byte pair encoding. That process of breaking text into common pieces like or ing.
Exactly. BPE finds frequent byte pairs and merges them into single tokens. It's a statistical trick to manage vocabulary size and handle rare words by breaking them into common parts. It's very efficient for many languages. But crucially, those BPE tokens often don't align perfectly with human semantic units. Token and utilization might be separate tokens, for example.
Okay, so the bias towards individual tokens works well when the tokens themselves are meaningful, like words or good subwords. What happens when they're not?
That's where the problems arise. When the data isn't naturally chunked into meaningful units at the token level, or when the data is very fine-grained, very high resolution, the performance of attention can really suffer. Think about character-level language modeling. Paying attention to individual letters T, H, E doesn't give you much semantic leverage compared to attending to the word V. Or consider DNA sequences. You only have 4 base pairs, A, C, G, T. There's no obvious tokenization in the linguistic sense. Trying to apply pairwise attention to every single base pair in a long genome sequence is computationally brutal and potentially not the best way to capture biological function, which often depends on longer motifs. And research confirms this. On tasks like character-level modeling or modeling DNA sequences directly, transformers often don't perform as well as other architectures. Sources show that state-space models can strongly outperform the transformer when data matched on these kinds of fine-grained tasks, often while using less compute. This suggests that SSMs, with their recurrent state, might be better at compressing this high-resolution, low-semantic content per unit data into more meaningful representations internally, rather than relying on explicit attention between potentially noisy or meaningless individual units.
So the transformer almost needs the data to be pre-digested into meaningful chunks via tokenization, otherwise its core attention mechanism struggles. It's not as good at building meaning from the very raw, fine-grained stuff.
That seems to be the case. It has a strong bias towards working with predefined, somewhat meaningful units. And this leads us directly to the tokenization bottleneck itself. This reliance on tokenization, usually BPE, is described in the sources as a pervasive handcrafted pre-processing step. It's this layer we stick between the raw data and the powerful neural network. And it has significant drawbacks. We've mentioned poor character-level understanding models struggling with typos, creative spelling, phonetics. Also, the tokens themselves often lack clear interpretability. What does BPE token #275FLE6 actually mean? It's often just a statistical artifact, not a human understandable concept. And performance degrades on languages that don't fit the BPE mold well, like agglutinative languages or logographic scripts like Chinese, where character boundaries are more fundamental than subwords. And it's awkward for non-text modalities like DNA or audio waveforms.
It feels like a workaround, almost. A necessary one, maybe, but still a deviation from the deep learning ideal.
Exactly. It runs counter to the core philosophy often called the bitter lesson, famously articulated by Rich Sutton.
Ah, the bitter lesson. Can you remind us what that is?
Sure. The bitter lesson essentially states that, historically, the biggest gains in AI haven't come from clever human-designed features or intricate model components. They've come from leveraging massive computation with simpler, more general learning methods. It suggests we should aim to replace handcrafted feature engineering like tokenization with end-to-end learning. Let the model learn directly from the raw data. Think computer vision moving from SIFT features to convolutional networks learning from raw pixels. That's the spirit. Ideally, we'd feed models raw bytes, raw audio samples, raw sensor readings, and let the neural network figure out the best representations. Minimize human priors, maximize learning.
So tokenization is a human prior, a feature engineering step we'd ideally like to get rid of, but we can't yet.
That's the current dilemma. As of now, the sources state that no end-to-end tokenizer-free model has managed to match the performance of the best tokenizer-based language models, given the same computational budget. So this imperfect pre-processing step, despite its known flaws, remains kind of indispensable for achieving today's state-of-the-art results with architectures like the transformer. It's a necessary evil for now, but overcoming it is a huge goal. Finding ways for AI to learn directly from the raw, continuous, messy data of the world is a major frontier.
Okay, putting it all together then. We have the quadratic scaling in training compute, the linear scaling in inference memory leading to hard limits, the finite context window problem, and this deep reliance on tokenization with all its associated issues. Given all these accumulating limitations, what's the big takeaway? What's the urgent call to action for the field? It sounds like we're really pushing up against the fundamental limits of this paradigm.
I think that's fair to say. The evidence strongly suggests that while transformers were revolutionary, they are, and I'm quoting the sources again, far from optimal in how they convert compute into capability. Their core design, global self-attention, explicit token caches makes them inherently inefficient for truly long sequences and less adaptable to raw diverse data without that handcrafted tokenization layer. This inefficiency and data inflexibility are becoming critical roadblocks as we aim for more general AI. Systems that need to process and understand the world's continuous complex data streams, long conversations, videos, complex scientific data, lifelong learning scenarios.
So this points towards an urgent need for fundamentally new architectures, models that need to be, let's list them. 1, computationally efficient, scaling linearly or near linearly with sequence length for both training and inference. That unlocks vastly longer contexts. 2. Memory efficient, maintaining a constant or at least very slowly growing memory footprint during inference, breaking free from that OL cache limit.
Mm.
3. Contextually robust, capable of maintaining truly long, persistent context, not just precise recall in a window, but summarization, abstraction, retaining the gist over arbitrary lengths, like that fuzzy long memory. And 4. Data agnostic, much less reliant on tokenization, better at learning meaningful representations directly from raw, high-resolution data, enabling true end-to-end learning across different modalities.
Absolutely. Those 4 points perfectly capture the desired properties. And this set of requirements is precisely what motivates the intense research into new foundations for sequence modeling. Linear recurrent models, and especially the modern class of state space models, SSMs, are emerging as really promising candidates because their fundamental design principles directly target these limitations. Their linear time processing, their efficient fixed-size state mechanisms. They offer potential solutions to the computational, memory, and contextual bottlenecks of transformers. And that's exactly what this series, Beyond Transformer, is going to explore. We'll dive deep into these alternatives, starting with the origins and concepts behind state space models.
Fantastic. So that concludes our initial deep dive into the Transformer's dilemma. We've explored its incredible power, but also dissected the significant scaling challenges, the memory constraints, the finite context issue, and that tricky dependence on tokenization. It leaves us with some really big questions, doesn't it? Can we actually break the quadratic scaling barrier? Can we build models that handle context lengths, orders of magnitude beyond what's possible today? And maybe more fundamentally, can AI learn to understand the world directly from its raw, continuous signals without us having to chop it up into artificial tokens first?
It really prompts a profound thought. What if the path to more capable, perhaps even more generally intelligent AI isn't just about building ever larger transformers? What if it requires fundamentally different kinds of computational brains? Architectures designed from the ground up to process information more like biological systems seem to fluidly, continuously compressing and summarizing the endless stream of messy real-world data. It's a shift from just scaling quantity to changing the quality of processing.
That's the exciting frontier we're setting out to explore in this Beyond Transformer series. Please join us next time as we begin that exploration by diving into state space models. We'll trace their intellectual lineage, starting with concepts like HIPPO for signal compression, and understand how they form the basis for a potentially new era of sequence modeling. We'll really get into their foundations.